So here is an example of a system of equations. 3x plus 2y equals -6. And -x plus y equals 7. So as we can see, it's a system because there's basically more than one equation. Now, what we're going to end up doing is we want to solve a system of equations. That means we would like to find values of the variables that can be substituted in and will satisfy all equations in the system. That's what we're going to mean by system or solving a system of equations. So you notice that we have both x and y going on here, and we're going to have to basically utilize or find something for both of them. They each need a little bit of something to be happy, to be satisfied. So what we're going to look at, there's two primary methods. We're going to look at something called the substitution method here. You solve one of your equations for one of the variables and substitute that into the other equation. In this case, the idea is that it would reduce the number of variables you have. So real quick, let's call this the original equation 1. This one will be the original equation 2. What I'm going to do is look at equation 2 here, -x plus y equals 7. If I were to just take this thing and add x to the other side, if I just did this little move here, well, notice now equation 2 would become y equals, well, we added x to the other side, so you're just x plus 7. And that may not seem profound, but now I can substitute this thing, x plus 7. I can substitute it into the other equation for y, because y is equal to x plus 7. So now I can look at equation 1 again. I'll have 3x plus 2 times y can be written as x plus 7 equals -6. And now that doesn't seem particularly profound, except that it is, because notice that equation 1 has now been transformed into something that only has the single variable x. X is my only variable going on here. So let's just solve this equation now for x. I would try distributing out the 2. So I'd have 3x plus 2x plus 14 equals -6. Then I would combine my x's together. 3x plus 2x will give me 5x. So it'll be 5x plus 14 equals -6. I just got to isolate x. It's really not that difficult. Kind of a standard problem. You'll get 5x equals -20. Divide both sides by 5. You'll get x equals -4. So I've solved for x here. I've gotten x by itself, and I've gotten it down to just be a single number. So I've done half the battle. In fact, I've done most of the heavy lifting. Because now x is equal to -4, we come back all the way to where we said y is equal to x plus 7. We substitute that -4 we found for x. And you can solve for y, and you'll get a y value of +3. Now, we have a numerical value for both x and y. We've solved the equation. We've solved the system, rather. We have found numerical values for each of them. But there's a simpler, more succinct way of writing this. You want to, if you can, when possible, write solutions as ordered pairs. So you can write it as the ordered pair. X is -4, so -4, comma, y is 3. And there you have it. This would be our solution. And that's all there is to it on that one. Not a whole lot more complicated than that. So -4, comma 3 written as an ordered pair, and it gives you the x and y values. So substitution is generally seen as pretty kind of straightforward here. We can work one more if you'd like. That one's in the books here. Let's try another system. 3x minus y equals -10. Here. There's our first equation. Our second equation, 3y minus x equals 6. Now, what you're going to learn is that you have two primary methods of solving these systems of equations. You can use the substitution method or the elimination method, which we'll learn in just a moment. How do you know when to use which one? Well, it just kind of comes down to experience. If you've worked a bunch of these, you'll kind of just realize what it should be. If you look at these here, if you look at these two equations, you can pretty quickly get one of these equations solved for just one of the variables. So if you pick on, say, equation 2 here, if I just add x over and then just subtract the 6 over, I can get an expression for x all by itself. And so that's going to be kind of what I'm going for here. So I'm going to take equation 2 here. I'm going to add x to both sides. Then I'm going to subtract 6 from both sides. And now I've solved equation 2, and I've gotten it in terms of x this time. You can pick either variable you want. This time I picked x to be the lonesome variable. And now I'm going to take this thing here, and forgive my John Maddenism, but I'm going to substitute it into the first equation, the other equation. I'm going to put it into x. because 3y minus 6 is exactly equal to x, and here's that same x floating around. So it's a very mechanical process. And we do this substitution method because now, just like the last problem, we have gotten it down to just one variable here. Now the only variable is y. So when we distribute this out, combine like terms, we can solve for y and just get a single numerical value for it. Ideally, just depends on how it works out. So let's distribute this 3. You're going to end up with 9y minus 18 minus y equals negative 10. Now let's combine our y's together. You should be getting 8y minus 18 equals negative 10. We got to get the y isolated, so I'm going to add 18 to both sides. So you're going to have 8y equals negative 10 plus 18 is positive 8. And now you'll just see that y is going to be equal to 1. Divide both sides by 8. Very simple. So we have our y value. Now we just need to get an x value as well. We know that y is equal to 1. We know we have an expression for x in terms of y. So just plug that 1 in for y to this guy over here. 3 times 1 minus 6 equals x. You should see that it'll be 3 minus 6 or negative 3. So my solution will be negative 3 for x, 1 for y, so it'll be the ordered pair, negative 3 comma 1. And that's our final answer there. So substitution method's pretty nice. Usually you can kind of just see what you need to do. What you need to do is get one of your variables isolated, substitute into the other one, solve it, and then substitute back into the other one. So it's a pretty straightforward process. It's pretty mechanical. And that would be our answer here. So that was the substitution method. Our next one, we're going to talk about the elimination method. The elimination method, this one has us adding the equations together, perhaps after being multiplied by some constants. That's the crux of the elimination method. Basically, all we're going to want to do is you can take either of your equations, you can multiply the entire equation by some constant. And as long as you do it to both sides of the equation, the equality is maintained, so you're not breaking any rules. You can also, this one's harder to see, you can actually add the two equations together. And I mean, you can line up the variables, line up the constants, and just add them together. The goal in doing that is that when you add them together, you end up eliminating one of your variables. So elimination is what we're going for. So let's look at an example of this. Let me find perhaps an interesting one among my notes. 3x minus y equals 9. So this one will look similar to the last thing we just had, but not quite. X plus 5y equals 19. So now we have this system. Now, ultimately, what we're going to want to do is we're going to want to add the two equations together. But first, we're going to make a modification. Notice if I add these equations together, let's just play pretend. And when I say add them together, I literally mean, okay, 3x plus x. So we're adding this equation. 3x plus x is 4x. Negative y plus 5y is 4y equals 9 plus 19 is 28. You can literally do something like this. But notice that by adding the equations together right at the get-go, I didn't really do anything. All I've got is now a new fresh equation that has both x and y involved. Instead, what I need to do with the elimination method, I need to multiply perhaps one or both of my equations by some kind of constant, so that whenever I do add the equations together, I'm going to completely eliminate one of the variables. And it looks like here you have negative y, here you have a positive 5y, but the point is, since they have opposite signs, if I multiply the first equation by a 5, leave the second equation alone, and I mean multiply the entire first equation by 5, I'm going to get 15x minus 5y equals 9 times 5 is 45. The second equation, I haven't altered it, so it's going to be the exact same thing. But now, by multiplying my entire first equation by a constant, which I'm allowed to do, as long as I did it to both sides of the equation. Now, when I add these equations together, something meaningful is going to happen. Now, let's see. 15x plus regular x is 16x, but negative 5y plus 5y, that's gone. Y is completely gone now, which is great. And then 45 plus 19, you might see, is 64. So bada bing, bada boom, I have eliminated one variable entirely. That's why it's called the elimination method. Now I just need to divide both sides by 16. And you might know 64 divided by 16 is exactly 4. Of course, you're free to do kind of old school division. And really, when you get to that point, you're like, 16 times what? You're trying to figure it out. And you'd end up seeing that 16 times 4 is exactly 64. So it works out cleanly with no, what do you call that? A remainder on division. So we get an x value of 4, of exactly 4. Now we need to deduce the y value here. And that's going to be easy. We can go back to the original equation. We can go back to the original system. We can pick either equation, either 3x minus y equals 9 or x plus 5y equals 19. Pick either one, substitute a 4 in for the x, and then solve for y. So I'll put it into equation 2 there. You'll get 4 plus 5y equals 19. Subtract the 4 over, you'll get 5y equals 15. Divide both sides by 5, you'll get y equals 3. So my final solution will be the coordinate 4 comma 3. And that's the answer. So not so bad when you look at it. Elimination, so substitution has us substitute one of the variables for the other. If I had to solve this with substitution, which I'm totally allowed to do, I would have taken this second equation, moved the 5y over, and then I'd have x equals negative 5y plus 19. Substitute that into the other one. Turns out you'll still get the same solution as long as you do it correctly. So you can actually use substitution or elimination to solve these equations. It's very useful to have both because depending on the situation, one might be a better or more quicker way to the solution than the other. Let's try out another one. And then we're going to start to get exotic with some of them. We'll see some kind of weird ones. Let's try this one. Uh-oh, we've got fractions involved. All right, that's not going to be the end of the world. Oh no, we've got fractions. Well, I mean, you can solve it straight up. You can leave everything as a fraction, and it will be kind of a pain in the butt. Or you could use a method called clearing out fractions. You're basically going to get rid of fractions completely as like a pre-step before you even try to solve this system of equations. For each equation, multiply both sides by the least common denominator, and you will clear out all fractions. That's going to be my tip to you. So we're going to clear out fractions. So we're going to look at each equation separately. We'll look at them separately. And again, this is like a preamble. We're not even talking about solving the system just yet. Well, let's see. We've got denominators of 2 and 3, again 3, in this system of equations, or in just this equation rather by itself. The least common denominator between 2 and 3 would be 6. Imagine if you were trying to get the same denominator, if you were adding these fractions. So actually what I'm going to do, I'm going to multiply the entire equation, both sides of it, by 6. All right, how's that going to look? Well, I'm going to have 6 times 7x, I'm going to have 42x, if you want to do it this way, over 2, plus again 42 now y over 3 equals. Now you might not want to do 6 times 91, so you can just leave it as 6 times 91, kind of dealer's choice here, over 3. In fact, we could have left this as 6 times 7x, 6 times 7y. Just kind of depends on how comfortable you are with simplifying fractions. Now you're going to have 42 divided by 2 can be written as 21. 42 divided by 2 is 21. So it can be seen as 21x. In fact, we multiplied both sides by 6 because we knew this kind of cancellation would happen to where we only have to deal with integers, whole numbers in each case. That's kind of the power of it. So this one's 21x. This over here, 42 divided by 3 is going to be 14y. Now over here, you have 6 times 91 divided by 3. The 6 and the 3 will have some cancellation, leaving you with 2 up here and just 1 on bottom. And then you need to do 2 times 91, which is 182. So even though the numbers just got a lot larger, that's not the end of the world because at least they're all whole numbers. At least we've gotten them down to whole numbers and there's no more fractions. So from this first equation, we've cleared out fractions. It's also called sweeping out fractions, if that interests you, to call it that instead. And so now what I'm going to do, I'm going to rewrite it in blue. I'm ending up with the equation 21x plus 14y equals 182. So this is going to be the equation I actually deal with, and we'll reproduce that in a moment. Next up over here, the second equation, you notice we've got denominators of 4 and 3. 4 and 3 are the denominators. The LCD of that is going to be 12. So I'm going to multiply both sides by 12. And this time I suppose I'll just leave the 12 written there. So it'll be 12x over 4 plus 12y over 3 equals 12 times 10 over 3. And now some cancellation can occur. That'll be a 12 divided by 4 is 3. 12 divided by 3 is 4. 12 divided by 3 is 4. Again, we did all that to eliminate the denominators. And that will leave us with the equation 3x plus 4y equals, the 12 and 3 are gone, but you still have 4 times 10, which is 40. All right, so we've swept out the fractions. Our first equation has now become this. Our second equation has now become this. The numbers have gotten a little bit larger, but at least we don't have fractions anymore, which is usually a good thing. So let's rewrite our system with the new equations we want to solve in play here. The first one will be this up here. The second one will be that down there. Now, technically, we can use elimination or substitution. It's just kind of your fancy. Just to give you another example of elimination, we'll use elimination. So it looks like 21 and 3, if I were to multiply this second equation by -7, that will kind of do what I'm hoping. Why? Because then this will become -21x. It'll have the opposite sign, but the same absolute value so that it'll get eliminated. So let's see, I'll have 21x plus 14y equals 182. For the second part, I'll have negative 7 times 3 will be negative 21x minus 4 times negative 7 will be 28y. And then 7 times 4 is 280. So 7 times 4 is 28. So 7 times 40 is 280, and it'll be negative. So now, if I add them together, the 21x minus 21x, that's gone. That was the whole point. Now this becomes 14y, basically minus 28y, which will give me negative 14y. And then next up, we're going to have 182 minus 280. Now we can tell that that's going to go negative. And because you're taking a larger number away from a smaller number. And then once you know it's negative, you do 280 minus 182, which would give you 98, but you know it's negative 98. Now you have to divide both sides by negative 14. Now that's not one of our common, we don't see 14 on the standard 12 by 12 multiplication table. So we might have to get a little clever here. We know it'll be positive because it's a negative divided by a negative. And so you're trying to figure out 14 goes into 98. Well, if you experiment around, you'll see that 14 times 6 won't end up being enough. But 14 times 7 will be enough. In fact, it'll come out perfectly. So you'll end up with a y value of 7 here, which is not so bad. The y value ended up being just a nice whole number. And now with a y value of 7, you can go into the original second equation. You could put a 7 in for y. You'll have 3x plus 4 times 7 equals 40. Taking this 7, substituting it in for y. You could have put it into the first equation here. You could have done 14 times 7, but notice that it would just get messy. The numbers are larger. If I use the second equation, the numbers are a bit smaller. So just kind of a prudent choice here. You'll get 3x plus 28 equals 40. Subtract 28 from both sides, you'll get 3x equals 12, and so x is 4. And so your final answer is the ordered pair 4, 7. So that one, the trick was to kind of just clear away fractions. Once you do clear away fractions, now you just have to deal with the elimination method. You could have used substitution method if that's what your heart wants to do. It may not have run as smoothly though. It might have been a little bit of a pain to do that. But that just kind of happens. Now, so far, all the systems we've solved have had a single solution. just a single ordered pair, and it was really easy. But there's extra possibilities. You can have no solutions to a system, which means you could say the solution set is the empty set. That's one possibility. There's no solutions, so there's empty. You could also actually have a weird case where you have infinitely many solutions to a system, in which case we're going to have to be clever. We're going to have to use some clever thinking to try and express the solution set. So these are two extra possibilities here. Let's investigate when you might run into these possibilities. What will happen is you'll run into the case of no solutions, where whenever you're trying to solve your system, either with substitution or elimination method, you'll run into an equation, in this case, that is false, but has eliminated the variables. You'll run into an equation like 1 equals 4 or -2 equals 7, which is clearly just false, and there's no variables in the equation to try and salvage it. You'll run into the case of infinitely many solutions when you end up with no variables and then you just get an arbitrarily true equation, like 4 equals 4, 0 equals 0, -3 equals -3. Not exactly helpful, but that's going to kind of be your clue that you're dealing with infinitely many solutions. So let's look at an example. 24x minus 8y equals 64. -3x plus y equals 8. So what we can do, you could try solving this with substitution if that's your fancy. Let's just try elimination, just because elimination is usually the preferred way to do it. Elimination has a lot of wonderful properties about it. If we were to do elimination, let's see, maybe we can pick x to be the variable we eliminate. So maybe if we multiply this second equation by 8, you'll see that you'll get -24x, which means you can add it and the x gets eliminated. All right. So we're going to have 24x minus 8y equals 64. And then I'm going to have -24x plus 8y equals 64 again. I seek to add these together. And now you'll notice something magical is going to happen. 24x minus 24x, well, that's gone. There's no more x's to worry about. But through something we could not escape, there's nothing we could have done about this. The y also gets eliminated. -8y plus 8y, I'm just left with 0 on the left-hand side of that equation. And there's nothing I can do about that. On the right-hand side, I'm left with 64 plus 64. I don't even get to do 64 minus 64, because then that would be 0, which might be a little nicer. No, I'm going to end up with that. This is a false statement. In other words, using proper mathematical means to solve the system led us to a clearly false, contradictory, if you will, statement. 0 equals 128 is ridiculous, but we didn't break any rules. We did everything according to the rules of mathematics that we have established so far. Whenever that kind of situation happens, you have no solution here. There's nothing that's going to work because no matter what you try, you're always going to end up with some kind of falseness. And there's nothing you can do about it. There's simply nothing you can do about it. And so that's it. Nothing that can be done for your case. So that is going to be the telltale sign of no solution. You, through proper mathematical channels, ended up with a statement that's nonsense and can't be salvaged. So no solution. How, though, could you end up with infinitely many solutions? The other possibility? Well, let's look at another system. 3x minus 4y equals 2. Negative 6x plus 8y equals negative 4. So let's look at this equation. And let's attempt to solve it using elimination. Now, looking at this again, if I multiply my first equation by 2, this will become positive 6x. We already have negative 6x down here. That's why I chose 2. And then when I add them together, my x is going to get eliminated completely, leaving me with 6x minus 8y equals 4. On bottom, negative 6x plus 8y equals negative 4. And now notice what's going to happen. I'm going to get, everything's going to be gone. When I add the second equation to the first. But again, there's nothing we could do about it. We are attempting to solve this properly. We realize we could eliminate x. It just so happens that we also are going to accidentally eliminate y. But there's nothing we could have done about that. It was already in the cards that that was going to happen to us, and we're just making the realization. 6x plus negative 6x will give you nothing. Negative 8y plus 8y will give you nothing. You're left with a big fat 0 burger on the left-hand side. On the right-hand side, you're going to do 4 plus negative 4. Again, you're going to be left with 0. Nothing that could have been done about it. You have done nothing wrong. In fact, you are completely in the right here. In the last case, we ended up with a false equation. We ended up with 0 equals 128, which is clearly not true. Here, though, we end up with a true statement. But this is called an arbitrarily true statement. It's true, 0 is equal to 0, but there's no variable involved anymore. We've completely eliminated the variables. Is it really interesting to you to say that 0 equals 0? Well, maybe you're not interested in any equations, but this one you're especially less interested in. Yeah, 0 is equal to 0, and the sun will come out tomorrow, bet your bottom dollar. Yeah, so it's arbitrary because it's just kind of uninteresting. I can say that any number is equal to itself, sure, that doesn't help me. When I reach something like this, it means I'll have infinitely many solutions. Now, that's the answer here. The way your homework and the way any exam question will want you to put that answer in, you will need to pick one of the variables to be the arbitrary variable. In this case, your homework or exam will tell you usually to pick y as the arbitrary variable. What this means is that we will let y be whatever it wants and solve for x in terms of y. So that's a long way of saying this. We're going to take our first equation here. We're going to say that the solution set whatever x is, we're going to say that y is arbitrary. So the solution is going to be written where we just have a y there. And then x, whatever x is, we need to have it in terms of y. So I'm going to take my first equation here. Oops. I'm going to take my, why are you doing this to me? Evil. There we go. I'm going to take my first equation here and I'm going to solve for x. I'm going to get x by itself. And there's nothing I can do to get rid of the y. It's just going to end up with y in it. I can add 4y to both sides. So I'll have 3x equals 4y plus 2. Now I need to divide both sides by 3. So I'm going to end up with x equals this 4y plus 2 over 3 business. And that is actually going to be my x coordinate in my solution. And that's exactly how I would write it. And what this is saying is that for this system of equations, I can let y be whatever it wants. I can pick any value I want for y. Then x is not allowed to be whatever it wants. X has to be sensitive to the value of y using this expression here. Thus, you can see, even though it doesn't look like it, that means there are infinitely many solutions because I can pick infinitely many numbers for y to be, and then it's just forcing x to be a certain value based on what I chose for y. And that's all there is to it. So the usual case is that you'll have one solution, but a lot of the times you'll also find that you can have no solution at all, or you can have infinitely many solutions. It won't be the case in a system of linear equations that you can have exactly 2 solutions, no more, no less, or exactly 3 solutions, or exactly 4 solutions. No, there are only 3 possibilities: 0 solutions, 1 solution, infinitely many solutions. Those are the only possibilities. Now, here's where we can get into something that's a little bit murky. We have systems of 2 equations with 2 variables. It turns out you can have systems of 3 equations, 3 different stinking variables. And so you're going to have to use z for a third variable. You're also going to find that these are a bit kind of long and cumbersome. Minus z equals 2. If you're going to end up, if you're going to have three variables here, well, the only thing that's going to make sense is if you end up with three equations as well. You need at least as many equations as you have variables if you expect to find some solutions, or if you hope to get to a single solution especially. So you look at that. This is a system of three equations with three variables. And you look at it and you say, well, just, oh joy, I'm just beaming with happiness here. Yeah, the reason that this one is going to be tough is that it's not going to fall down in just a single substitution or just a single elimination. You're going to have a little bit of work ahead of you uh, if you hope to, solve this equation. And there's not a whole lot we can do about that, but that is just kind of life. What you got to do is you got to grind it out. You can use elimination, you can use substitution. The path is not always guaranteed before you. It's not always obvious what you want to do in each case. So it just kind of depends on your intuition here. I would argue that substitution might be the easiest system here. What you're going to want to end up doing is you want to end up eliminating one of your variables completely and ending up with two equations with only two of the variables involved. And you can accomplish that in a number of ways. Let's see. Let's take equation 3 here and let's solve it for x. So I'm going to write out my steps. I'm going to isolate x here in equation 3. Well, I would need to add y to the other side and subtract z from the other side. So it's going to be positive y minus z plus that 1 that was already here on the right-hand side. Now, in doing that, what I'm going to do is I'm going to substitute this new equation 3 into equations 1 and 2. That just seems to me like a sound method, because then equations 1 and 2 will no longer have the x variable, they'll only have y and z. And now I've got it down to just two variables and two new equations. So I'm going to take this y minus z plus 1, I'm going to substitute it in for x up here. I'm going to take y minus z plus 1, I'm going to substitute it in for x in equation 2. So equation 1 is going to become, instead of x, I'm going to have y minus z plus 1 plus y plus z equals 7. And let's see if that does anything for me. It looks like we're going to get lucky here. And we don't often get lucky in mathematics, but it looks like that's going to be our case here. Let's see, you have y plus y, you're going to end up with 2y. You have negative z plus z. Your z actually goes away. And you just are left with 2y plus 1 equals 7. You should be chomping at the bit when you see something like this, because now you're going to see that you get to just solve for y and get it down to a single number. You'll get 2y, move the 1 over, 2y equals 6, divide both sides by 2. You'll get y equals 3. Ooh, that's awesome. I'm going to come down and I'm going to store this over here. Now, we substituted into equation 1, and that led to some really positive results. We ended up getting one of our variables solved for. That doesn't always happen. We might end up with 2 variables there still. Now I'm going to substitute into the second equation. I'm still going to substitute this thing in for x in the second equation here. I'm going to end up with 2 times y minus z plus 1. So 2 times the x thing plus y minus z equals 2. Now I'm going to distribute the 2. I'll have 2y minus 2z plus 2 plus y minus z equals 2. Combine like terms, I'll end up with 3y minus 3z plus 2 equals 2. And then I can move the 2 over to the other side, which coincidentally is going to just give me 0. So this is what equation 2 has become after I did that substitution. But wait a minute, I've got some good news for you, because y is just equal to 3. Y is just equal to 3. So I can substitute that in here. 3 times. I know that y is equal to 3 no matter what anyone says. 3 times 3 minus 3z equals 0. 9 minus 3z equals 0. It's not as bad as it looks anymore. Subtract the 9 over, negative 3z equals negative 9. Finally, divide both sides by negative 3. You'll get z is also equal to 3. So what once looked like a very difficult system is slowly starting to become unraveled. I've got a value for y is equal to 3. By coincidence, z is also equal to 3. That makes me very happy. Now, I just need to solve for x somehow. And I'll have all 3 of my variables. Notice, though, I've already on the board have written an equation for x in terms of y and z. So I just need to take this thing, x equals y is 3 minus z is also 3, and then that plus 1 that's there. And you'll clearly get x equals 1. 3 minus 3 is 0 plus 1. So I've solved it. It wasn't quite as bad as it looked. It involved a little bit of playing around at it. I can't promise you'll always find the most efficient path right off the bat. In fact, whenever I work these, I kind of have to sit and think a little bit carefully so that I can work them succinctly without taking up a ton of board space and making it all complicated. But sometimes you just kind of get lucky. Now, how to express the solution? Well, earlier we had an ordered pair that had an x variable and a y variable. Here we just extend that, an ordered triple, x, y, and z. So if you only have 2 variables, use an ordered pair. If you have 3 variables, you have to use an ordered triple. And so that will be 1, 3, 3. That will be our solution. And that's literally exactly how we express it. X is 1, Y is 3, Z is 3. So we can solve a system with 3 equations and 3 variables. You just kind of have to sit and think about it and work your way through it slowly, and it'll just kind of unravel in front of you. Notice I'm using a lot of green and red, and that's not a coincidence. It's because Christmas is coming up, and that makes me very excited. I love the holiday season. I enjoy it very much. When I was younger, when I was about your age, I hated Christmas. And then one day I literally just said, Josh, everybody loves this holiday. It's a lot of fun. Quit being a jerk. Quit ruining it for everyone. I'd always say, oh, Christmas is about materialism. But as I've gotten older, I've realized materialism is great. What are you talking about? All right, I like having things. Okay. No, I'm just kidding. Anywho, we can solve an interesting one here. What we're going to do is, well, here, I'll just kind of express it in a fun way. Write the parabola We'll figure out the parabola written in terms of y equals ax squared plus bx plus c. Write the parabola y equals ax squared plus bx plus c that passes through the points. I'm going to give you 3 coordinates that this parabola passes through. 4, negative 53. The next point it passes through is negative 4, negative 37. The last point it passes through is negative 3, negative 18. So it passes through these points. Maybe I'll just space them out. Wait a minute. What in the world? What does this have to do with systems of equations that we've been solving so far? Well, Pilgrim, I'll tell you what it has to do with systems of equations. Basically, when the parabola, you have 3 points here, the x value of 4, a y value of negative 53, an x value of negative 4, a y value of negative 37, an x value of negative 3, a y value of negative 18. You can actually use this information to figure out what these coefficients must be, A, B, and C. And it's kind of a neat thing. So consider this first point here in green. For an x value of 4, you get a y value of negative 53, excuse me. So wait a minute, I'm going to get negative 53 for y equals whatever A is times 4 squared plus whatever B is times 4 plus whatever C is. That's exactly what it means for the point 4, negative 53, and this is supposed to be for a parabola. So what we're going to have time to do today is I'm going to have time to set this up for you. We may not have full time to solve it, but you have seen an example of solving a 3x3 system. Next up, check out this second point. This second point says you have an x value of negative 4 and a y value of negative 37. So that leads you to the equation y is negative 37 equals whatever a is, whatever the coefficient of the x squared term is, times negative 4 squared plus whatever b is times negative 4 plus whatever c is. And then finally, in orange, this third point that we have here, x value of negative 3, y value of negative 18, plug those x and y values into this, into the basic form of a parabola. You're going to have negative 18 for y equals whatever a is times negative 3 squared plus whatever b is times negative 3 plus whatever c is. So notice we're actually kind of like flipping this one on the head. We want to know the parabola that passes through these points. We need to figure out what A, B, and C are. Because we know the final answer is going to be y equals something x squared plus something x plus some constant. This is exactly how we would set it up. Only notice now our three variables that we don't know are A, B, and C, the coefficients of the parabola. And we have everything we need here to be able to solve this. So we're going to end up being able to create, I need a little more space over here. Oops. We're going to end up being able to create a system of three equations with three unknowns. This first equation will basically become, let's think about it, 4 squared is 16, so it'll be 16a plus b times 4 is 4b plus c equals negative 53. That's another way of writing this first equation. Just kind of simplifying it, putting my variables on the left-hand side, which is where I usually like them. This second equation, negative 4 squared, is again 16a minus 4b this time, plus c equals negative 37. And then finally, this last equation, negative 3 squared is 9, so it'll be 9a, b times negative 3 minus 3b plus c equals negative 18. So now what we're really doing, we haven't found the solution, but we just want to solve this system for A, B, and C. And then express your final answer as the parabola. Your final answer will be y equals whatever you get for A, x squared, plus whatever you get for B, x, plus whatever you get for C, the constant. So unfortunately, we don't have time to solve this one because you have to explain it as you go. That takes more time. One tip though, a tip for you. Notice how these first and second equations are very similar. What you can do is if you just subtract the second equation from the first one straight up, you will, by coincidence, eliminate two of your variables. So if I subtract the second equation from the first, 16a minus 16a, the a goes away, the b will not go away, the c will go away. So you'll just have a single equation with a single variable, b. You can solve for b really easily that way, and that will kind of help to unravel the rest of it.